Hello, welcome to Always Curious. Today I'm going to talk about one of our favorite topics. It's called Create, Push, and Poof, It's Gone. This is a chapter in this book, Fundamental Informationals, which is one of 3 books in our informational series. And actually, the chapter right before this in the book is called Phantasmagorical Story that is the true state of physics today. And what that chapter is about is it's actually our derivation of quantum field theory, plus a bunch of other stuff in the book. But the derivation of quantum field theory is, I think, quite interesting. So what does quantum field theory say? It says for each elementary particle, like an electron, there's a field. So there's an electron field. It might look like this. And for another elementary particle, like maybe a photon, there's a different field. Okay, so here's the potential photon field. And they go through all space. And if I'm going to make a particle, right, let's say I'm going to make an electron right here at the tip of this gun, what that means in quantum field theory is to create a particle, the field is excited. So I'm going to excite the field. Here's an excited field. And that represents the particle right here at the end of the gun. And then we're going to shoot the particle at the wall. But what happens when the particle starts moving? Well, something very interesting happens. Poof. The particle disappears. It's no longer a particle, and it's governed by what's called the time-dependent Schrödinger equation. And we talk about the time-dependent Schrödinger equation in the book up here, Lifting the Enigma Shroud from Quantum Mathematics. We also, however, talk about the time-independent Schrödinger equation in this book, and they're completely different. And almost nobody ever acknowledges the difference. The time-independent Schrödinger equation we deal with in chapters 1 through 4 in the book. So, but what does the time-dependent Schrödinger equation say about this electron that we just created here? It says that the electron turns into a mathematical entity. It's no longer an electron. It's a mathematical probability wave in configuration space, whatever that means. And what that tells us is the probability of where the particle's at. And it could be here. There's a probability for being here and 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 everywhere in space. But the probability is greatest, of course, along the line headed towards the wall. But the prop could be here, could be here. But then right when it gets to the wall with high probability, guess what happens? Another poof. And now the probability wave goes away, and there's an electron at the wall right here. So it turns back into an electron. Well, does quantum field theory say it turns back into an electron? No. Does the time-dependent Schrödinger equation say it turns back into an electron? No. No one knows how it turns back into an electron. That's called the measurement problem. So does the wall measure the electron or measure the probability wave and turn it into an electron? Or does an atom in the wall do that? Or do we have to have some device at the wall that measures it, and that device is being looked at by a conscious person? Some people think that. Nobody knows. And this is supposedly the biggest problem in physics, or one of the biggest problems in quantum physics, the measurement problem. What governs the measurement problem? But we think this other stuff, these probability, an electron turning into a probability wave, That's not a problem? No, that's a problem. And quantum field theory, creating a particle as an excitation of a wave, that's probably a problem. So none of this, quantum field theory, the time-dependent Schrodinger equation, tells us anything about reality. And the measurement problem just points out how all of this really does not give us a road to reality.